Designing and tuning cameras for visual image quality is hard enough for expert imaging teams, but doing so for best computer vision performance is not possible with today's approaches. I look forward to showing you how you can use the Atlas Camera Optimization Suite to address this challenging problem. My name is Marc Courtemanche, and I'm product architect for Atlas at Algolux. Atlas is the first automated tool that optimizes a camera's ISP parameters to maximize computer vision accuracy. It is able to improve vision performance as measured using mean average precision by up to 25 points in only days. No additional training or rework of the model is required to achieve these significant results. Atlas delivers its optimization capability as a cloud service, interacting with an on-premise Atlas client that manages raw image data sets, processing of those images by the ISP and CV model, and KPI calculations. Throughout this process, your image data and CV models are kept securely on your premises. Only KPI metric values are sent to the Atlas server in the cloud, which returns the next set of ISP parameters to the Atlas client for processing. This architecture lets you easily scale across different teams and concurrent programs. Atlas also provides a framework of base components so you can easily connect your own ISPs, CV models, and KPIs into the workflow. So how does Atlas work? Let's look at the Atlas client in more detail. We see that it interfaces with local data storage as well as with specific user components associated with your target ISP, CV model, and KPIs. As we dive into the tutorial, you'll see how these components are explicitly instantiated as Docker containers and used in the Atlas optimization workflow. Let's go to a terminal on the demo machine. We'll be deploying the Atlas client components on a standard Linux PC with a 4-core, 8-thread CPU and an NVIDIA GPU. The GPU is used to accelerate the YOLO v4 CV model used in the demonstration. Since components interact over the network, the deployment architecture is compatible with distributing components across multiple cores, GPUs, and machines. Let's set up the components from the terminal using a script. We see our 4-core, 8-threaded CPU, our NVIDIA GTX 1080 GPU. Pre-built on the machine are Docker images for ISP, YOLO v4 CV model, and CV tools used to compute the KPIs. We now launch the various components. Start by launching an Atlas runtime storage instance, which is basically a database. We then run a GPU-accelerated YOLO v4 model instance and the CV model tools. Finally, we launch 4 instances of the software ISP. We will then launch the Jupyter UI interface. Once the Jupyter UI is launched, we can access it to run our optimization Python script interactively. Let's go to the browser. With the notebook loaded in Jupyter, let's run it and quickly walk through the steps required to run the optimization. We start by loading the Atlas AX packages, which provide the framework for orchestrating the optimization. We then read from the disk the set of raw images and the JSON-formatted ground truth object annotations. For this demo, a small dataset of 38 raw images captured with an off-the-shelf camera module using a Sony IMX290 sensor is used. We then instantiate our 4 ISP instances within the framework using the proper ports. We then define some convenience functions to manage the ISP and populate the ISP settings derived from measurements and calibration that will not be optimized. We then configure the ISP, CV model, and CV tools to store and save data using the Atlas runtime storage. The user then establishes a connection with the Atlas server in the cloud using their credentials and creates a cloud optimizer instance and retrieves the run identifier referencing the optimization run. We define the ISP parameters to optimize in their range, define the correct CV model as a preprocessor, and set the mean average precision KPI with the target of 1, a perfect score, to drive the optimization. These parameters are provided to the client object, which is then used to run the optimization, in this case for 1,000 trials. The optimization will run as a background process while outputting logs to the notebook. It can be terminated at any point and the cloud resource is freed directly from the notebook. As we are limited in time, I did not cover the Atlas Cloud user interface through which optimization run results can be managed, monitored, and analyzed in the cloud. We do have a webinar covering this topic, so feel free to reach out if you'd like to watch it. We end the presentation by taking a look at how one of our customers, an automotive tier 1 developing a forward-facing vision system for a large OEM, used Atlas to improve the OEM's computer vision accuracy. The imaging pipeline used a Sony IMX490 5-megapixel image sensor and the Renesas V3H ISP. The sensor was configured to capture an HDR image with a 24-bit linear range that was piecewise linearly compended to 16-bit for input to the ISP. An image set of 2,500 images covering a range of lighting and weather conditions was quickly captured by the customer. Of those, just 90 images were needed for the optimization set, and the rest was used for validation. In just days, the ISP optimization resulted in substantial improvements, especially in low light conditions, where optimization improved the CV detection's mean average precision score by up to 28 points over the baseline image quality tuning provided by the ISP vendor. This is the end of our presentation. Thank you very much for attending, and please contact us at Algolux for more information.